So it's my great pleasure to introduce Ian Price, who's going to tell us about implicit automata in lambda-calculi 3.
Yeah, hi. So yeah, my name is Ian. I'm a PhD student at Swansea. This is joint work with my supervisor, Cécilia Pradic. I guess the first thing to do is to apologize for the title. It's kind of a word salad, right? Implicit automata, affine, planar, string-to-string functions. But you don't need to have seen parts 1 or 2. I'll just sort of explain a little bit about what I think that means, and then I'll get into the talk. So when I think of what implicit automata means, I'm thinking about trying to characterize automata in logic or in the lambda calculus, and ideally being able to take your lambda terms and convert them back into an actual automaton, because going the other way is usually not too much of a trouble. So the story is kind of starts with this paper by Hilbrand and Kanellakis in '96. And it gives a bunch of characterizations of things in computability. There's they characterize p time, p space, not NP. But for our purposes, regular languages can be characterized in the simply type lambda calculus. Basically, if their characteristic function is definable in an appropriate sense. And what do I mean when I say strings and bools in an appropriate sense? I mean church encodings. So I suspect most people here are familiar with this, but the short story is that you can represent basically any algebraic data type as a function. In the case of true and false, every closed term of this type is either beta eta equivalent to either true or false. For strings, the way we get this is by viewing strings as a type with n+1 constructors, n constructors that const letters onto the beginning of the string, and something for epsilon. And again, up to beta eta, everything is of this form. So they're using one of the constructors in this sort of linear tree fashion. And the append is just an example that I'm going to use on the next slide. It's not particularly important. But how would you go about proving this theorem of Hilbrand and Kanellakis? Well, one direction's easy. If you've got an automata, you can sort of code up the transition function pretty easily in a lambda calculus. But the other direction requires like a bit more work. The arguments in this case, a kind of semantic interpretation. So we interpret the base type by this 2-element set, function types by function spaces, terms by the lambda terms by the obvious functions. And when we now look at terms of this type, we can then consider the interpretation of all the strings that you can make from that type. And this gives a finite but pretty large set. And this is a very quick little exercise to check that this actually gives the right automata. And the key observation is that as you progress through the automata, essentially the space you're at is the interpretation of the church encoding of that string. And obviously, infinitely many of them are getting smooshed down into finitely many pieces. So that's 1996. What about 2024? So this is where the word salad comes in, right? We have affine string-to-string lambda p definable functions, and these are equivalent to first-order transductions, which I'm not going to mention, except that these are a thing people study. It's one of the better-known classes. And planar reversible two-way finite transducers. I'm going to explain what those are in a little bit. But the latter two was previous work of my supervisor and her collaborator, Tito. And the new stuff is relating them to string-to-string definable functions. So what are those? I tried to condense it onto one slide. I don't know if I succeeded very well, but we'll see. So we're working in a non-commutative affine lambda calculus. There's no point giving like all the term rules. These three examples cover the adjectives. So the first one, the one with the tick, in a linear logic, you would have to use X, but in an affine thing, you get to throw stuff away. Bob talked about this earlier today. But we do still forbid duplication. So this second one here is not typable. And similarly, The third one isn't typable because the term in your body of your has to use the variables in your context in the same order that they appear. And some of the so now we have two arrows. These are all the linear arrow. This is just because this is how we're going to be handling generators in a little bit. So our contexts are split up into linear and affine and non-affine parts, and we need to adapt the notion of a string. Each of these constructors now has a linear or an affine arrow instead, but we do have to keep the non-affine arrow here because you need to be able to call the constructors multiple times if you want to generate all the strings. And so affine definable means that we have a string-to-string function is affine definable if there's a lambda term from string lolly string that computes the same thing up to equivalence of church encodings. And this kappa here is a purely affine type, which means you don't get to use this regular arrow. You're stuck with the fragment that uses the affine lolly. So that's affine string-to-string definable functions. What about two-way automata? So again, no definition, just a picture. Well, another picture on the next slide. But a two-way automaton, in this case, you can think of as a Turing machine where you have a read-only input tape and a append-only output tape. So each of our transitions has a thing you read and a thing you output. And two other little things to notice are these bumpers, these triangles. These are markers for the beginning and the end of the word, so you know if you're at the beginning or at the end. And because you can go in both directions, we now have states are partitioned into forward states and backward states, which tell you how to advance the tape. So this is about as complicated as an example as you can fit on a slide. But while I like this picture, I want to show you another picture, which I'm for about 2 slides. So that's going to be annoying for you, I suppose. So instead, I want to think of these as functors. And so I want to consider each of the letters in the alphabet, the 0, the 1, the 2, and the 2 bumpers, and think about how this function operates on this maps from states to states. And because we're going to be talking about reversible and planar transducers, that's going to correspond to, well, reversible means that each of these things have degree at most 1. So things can have either an arrow going to them or going to them. You kind of 2 going in, you kind of 2 leaving. And planar means planar. Arrows in these diagrams don't get to cross. But I assure you that this is the same diagram as the previous slide, just in a more microchippy form. So if as I said, I want to express these things as functors for reasons that will become apparent in a second. If you were here on Tuesday, Daniela Petrusan gave a talk at the Logic and Semantics seminar, where she defined, where she talked about this notion of an automata as a functor and gave a whole bunch of examples. So this picture comes straight from her. You have the freely generated category on this image, and you have n+2 generators, 1 for each element of your string, plus 1 for the bumpers. And the nice thing about this category is that words in your language correspond to morphisms from in to out, just by composition in the obvious way. So with that category, this is a sensible definition of an automaton. An automaton is a functor from that category to some base category, along with decisions have to be made about input and output. So the only example, well, there are 2 examples in this talk. One is this deterministic finite automaton example. I fleshed this out a little bit more if you were at BCTCS. You got the gentle version. But if you unwind the definitions, set automata from singleton to binary give you the DFAs, because this is your the singleton gives you your initial state, the binary one gives you your final states. Cool. And so it's not immediately apparent when you look at a picture like this that you can actually do this. because this category here looks like you're just processing it start to finish. So we need to cook up something a little bit more complicated. So we have to cook up something more complicated that lets us go backwards and forwards, and that encodes our constraints of reversibility and planarity and the ability to output strings. So we have this category of what I've termed transition diagrams. This is related to the int construction that Samson Abramsky talked about yesterday. So objects in this category are binary words. These pluses and minuses correspond to the forward and backward states. And I say words, we have now put an ordering on these. That's kind of important when you're doing the planarity stuff. And morphisms are special diagrams. So I like this picture because it sort of encodes all the cases that can happen. So when you define the configurations for two-way automaton, it really matters whether you're going from a forward state to a forward state, because then you have to advance the tape forward. Those correspond to plus arrows, and they must go from the left-hand side to the right-hand side. Similarly, if you have a backward state to a backward state, minus to minus, so you can go backwards in the tape. And if you go from a forward state to a backward state, you essentially like stay where you are, but pay attention to what the letter is. And that corresponds to these two cases. If it goes from plus to minus, it stays on the left-hand side. If it goes from minus to plus, it goes on the right-hand side. That's a mouthful, but after 10 minutes of drawing them, you'll never draw a wrong picture, probably. We'll see. If it's a category, I've got to be able to compose it, right? So the obvious thing you want to do is just glue them together, but that's a bit fraught. It mostly works. So in the case of like this bottom one here, that's this plus going from C to Z to B to output, and you're concatenating as you go along. But there are these two weird cases. You can have this little loop that can occur, and you can have things that dangle into the middle. And you'll notice that they are not in the final picture. So the there are separate justifications for each of these. So the loops can be ignored because you can't get into them and you can't get out of them because of this reversibility constraint. So from a point of view of looking at the semantics of an automaton, you can just ignore these. They don't exist. Well, they exist, but they don't matter. This case, the minus to minus that dangles in the middle case does matter. Essentially, this comes about because when you define these automata, they define partial functions. You only output a word if you end up in a final state. And there is a sense in which I think of this as encoding that. Trust me. Identities are just going to be straight arrows across. So there's nothing very interesting there. And so now that picture that you saw earlier with the 5 slides, a planar reversible transducer is a functor from the shape category to transdiag. If you were at BCTCS, I said it was from plus to plus. We changed that to make the proof a bit easier, but there is an equivalent characterization. Now we start off in the empty word and end up in a plus minus word. It's just the same by yanking a wire around. Yeah, and just before I sort of move on a little bit, the category is very nice. It's strict monoidal. You get to compose top to bottom. There is an ordering on diagrams by inclusion. So this is what this poset with bottom enriched means. Bottom because there's a trivial diagram with no wires between any two words. I had to look up what the name of the structure we actually found was. I ended up having to look in Selinger, and the phrase we ended up with was pivotal category. But what I keep saying is non-symmetric compact closed. We have a notion of dual given by maps that look like this. This is the eta rule for minus plus. And this dual one lets you rotate diagrams 180 degrees. And the reason that we care about this is because this is a pretty good category for interpreting lambda p. If we think of compact closed categories as being like a place to do linear logic, then a non-commutative compact closed thing should be suitable for doing non-commutative linear logic. And it is. Here's the translation. Do not pay that much attention to it. If you know how it works, then you don't need to read the slide because you know how it works. If you don't, you're probably not going to get it in the time the slide is up. But these two are just application and lambda come from monoidal closure. And the only two annoyances are, so I mentioned that our contexts have to be split into a nonlinear and a linear part. The nonlinear part lets us handle the generators. Those are what let us generate the strings in the first place. That's given by this rule up at the top. The rule in the second case is for selecting variables. Those bottoms let you just filter out all the everything else. So I claim this is a good translation. Is it a good translation? Kind of, yeah. So we want related lambda terms to go to related diagrams. And if we have a Anita expansion, it's equality on the nose. This is just the snake lemma for duals. For beta, it's a little bit more complicated because of this dangling into the middle case. When you do an apply, you could end up with something in the middle, and then the wire is being deleted, so to speak. So then you get a strict inclusion of diagrams. But it's still nice, right? If we normalize our term, then we get a strict subdiagram, and that's, for our case, enough. So I said a lot of things, but this, just to remind you, this was the goal. I wanted to show that affine string-to-string, lambda p definable functions, and planar reversible 2H finite transducers do the same sort of thing. And just like with the Hilbrand-Kanellakis case, I'm only going to go one direction. The other one is, you can ask me at the end. So it's I'm going to keep it high level, right? So we start with a lambda term of type string to string, and we have a lemma that says up to beta eta, these are nice. And by nice, I mean all they can really do is apply the string with some specially chosen lambda terms and do some post-processing. So we end up with this this n plus 2, the n plus 2 from earlier, closed terms. And so that seemed like a good candidate for our functor. And we apply the translation, and we get something that is almost but not quite right. Because those were closed terms, we have this I at the beginning, which is not what we wanted, but we still have this adjunction, so bippity boppity boo. So that's a functor. Is it the right functor? Well, we need to do a little calculation, and again, tremendously abbreviated. The magic happens. That's all applying universal properties of like the monoidal closure and stuff. The important thing is that you end up with something that's just applying these DWs in some order and then taking the interpretation. Because this is a function from words to words, we know that our output at the end is a church-encoded string. So when we normalize the term that's inside of this interpretation, we should just be getting the church string. And so we're getting a strict subdiagram, as we talked before. And diagrams of church-encoded words are very simple. They just go from I to minus plus with the appropriate label on them. And this is secretly equals because if this is a subdiagram of this and they have the same type, well, it has to be. There are no other places to put the words, right? There are no other places to put arrows. So this is an equality. And there, now you don't need to read the paper. So the other direction is applying this sledgehammer called the Krohn-Rhodes decomposition theorem. Basically what it says is you take your automata, you apply this, it splits up into a composition of nice automata, and then you just check that nice automata are representable by lambda terms and that nice ones compose. And they do. Read the paper. If you're interested, dropping planarity would give you like an actual compact closed category, and then the result just lifts from first order to regular transducers. And this is kind of like an awkward fit. I'm very bad at wrapping up talks, but before we were thinking about string lolly string, so you only get to use the string once. But a thing that was in the paper and then had to be taken out because it wasn't fully fleshed out was that we think these are equivalent to things called comparison-free first-order functions. So coming soon. And yeah, just I wanted to leave you with like a broader picture because like the point of this is to do this in a whole bunch of different cases, see what you get. So this was the Hildebrand and Kanellakis case that says simply typed string-to-bool things are regular. This is also true for linear and affine. Work of my supervisor with Tito was that if you do this in the non-commutative case, you get star-free, so a strictly smaller class of languages. And then we also have, and then some of this is just what I've been talking about today. And here are the things we don't know. So we can thank my supervisor for this slide. We have reasons to believe that this is polyregular. The description of this is, I think, regular intersect some condition on the Parry images. But this is where we're thinking. This is the state of things where we're at. So apologies for blitzing through that. But yeah, everything I've said is in the paper or in one of these. These slides are available at countingishard.org. I'm really fond of that URL. And thank you very much.
Questions? The order is a bit reversed when it comes to with words. It's really to regular and then to understand what's the start situation. You're in person, you have first order design things, and then you are wondering about.
Well, I guess that depends on whether you think non-commutative is like easier or harder than the commutative case, right? Because like, I mean, in some sense, I'm not sure that I have any like particularly like good insights into this, except yeah, I'm not sure that I have a good answer. I'm afraid. Sorry. Jack.
So your category was right closed, right?
It's closed on both sides. Yeah, I mean, there's no. I don't have like a good picture, but like it's like it's properly autonomous. It's you have both. You have both.
You could restrict it just to one side, and that might change things, or?
Well,
It goes both ways.
Yeah. Yeah. I mean, I guess it's just one of those things that like we just haven't thought about. Like the reason that you start thinking about these things is that you start thinking about like, well, what's like linear logic like, and then you weren't trying to think about like specifically like rigid or things like this, but I suppose so. Possibly.
Any other questions?
I can't think off the top of my head what you're talking about, so I can't answer the question. No, it's perfectly understandable. Yeah, apologies for not being more helpful.